All right. My name is Bo. I'm with the Google Research, the Brain team. Our team focuses on developing new recommender system techniques, and we collaborate with different product teams within Google to improve their recommender systems. So today, I'm very excited to share our recent work on latent user intent modeling for sequential recommender systems. So we have a manuscript available on archive, so feel free to check it out if you want to know more about the details of the technique. So I'm presenting today on behalf of our collaborators within the research team and the product team inside Google. So a little bit of the background here. OK, so a little bit of the background here. So sequential recommender systems are a class of recommender systems that essentially are based on modeling the order of user item interactions. So for example, if you think about the e-commerce website, the user interaction history could be the history or sequence of transactions or a history of browse history or things like that. And by using the sequential recommender system technique, we are essentially using a sequential model. It could be either an RNN or a transformer to capture this user interaction history and then get a user representation. And then based on that user representation, we can recommend new items or topics that the user might be interested in interacting next. So that's the high-level summary of a sequential recommender. But one downside of the commonly used recommender system is that it's mainly based on the item-level interaction history, right? So the model knows what items the user consumed before, but those topics or item history are very good to capture topical interest. But on the other hand, we often lack a higher level understanding of users' intent. So here, by user intent, what we meant is what the user actually wants from the platform at the request time. Again, because the information we know about the user is only based on the item history, but we don't really know what the user wants from the platform. So some examples of user intent could be like exploring some new topics or some new content, or to continue consuming the contents from the last session, or even to play some background noise or background music, things like that. And yeah, so this intent, in the literature or existing work, intents could be explicitly defined. For example, in the search literature, people have been classifying search intents into 3 categories. That is the navigational, transactional, and informational intents. So we can do something similar here to capture user intent in the recommender system setup. So essentially, we are making this a supervised learning task by defining different sets of user intents. So one advantage of this kind of approach is that it will have very good interpretability, because essentially it's a supervised model. We know exactly what the model is predicting. And then on top of that, we have pretty reliable evaluation metrics for the supervised learning task or classification models. But on the other hand, the downside is that to model user intent explicitly, that would require some extra knowledge to manually define those user intents, like the example we just talked about that. So that would require some expert knowledge to do that. And also, human behavior is quite complex. Sometimes the manually defined intents might not truly reflect the complex user motivation. And also, it will be very challenging to enumerate all the possible user intents. So that motivates us to tackle this problem from a different angle. Sorry. OK, so yeah, that motivates us to tackle this problem using a different approach. So this so-called latent variable model is very commonly used in statistics and machine learning and other social sciences. So essentially, it's a probabilistic modeling approach that can relate a set of observed variables to a set of latent variables. So one common example or typical example is the so-called factor analysis. So imagine you have the observation of a say you have a class of students, and then for each student, you can observe the student's performance, academic performance on, say, 10 different subjects. But you can make an assumption that the performance on those 10 subjects are actually dictated by, say, two latent factors. That could be the mathematical aptitude and reading aptitude. That's actually a commonly used assumption in social science. So basically, we're assuming that although we have like 10 scores that we observed for each student, but underlying those 10 scores, there are two numbers that are dictating the performance on the 10 subjects. So the 10 scores are the observed variable here, whereas the 2 scores are the latent variable here. So we can infer the latent variables from the observed score. So that's a very simple assumption, a very simple example for latent variable model here. But again, on a high level, it's a probabilistic model that can relate some observed variables to some latent variables. Another insight we have here in order to model user intent is that user behavior signals on an online platform are often good indicators of the underlying user intent. So one example is that, let's say I'm waiting for a subway to go to work, and I only have 3 minutes to spend some time on a video platform. So if that's the case, I might choose to browse more and then choose to watch a video that is shorter. Whereas on the other hand, if it's a Sunday afternoon and I'm staying at home, I might choose to watch a very long video, like 2-hour background music video, to play in the background while I'm doing something else. So basically, the thing is that if we can make use of a user behavior signal to help us better understand user intent, that would be very helpful. So based on those two insights, what we are proposing here is essentially to use latent variable models to relate the user behavior signals as the observed variables, and then to infer user intents as the latent variable. So that's the one-sentence summary of our proposed method here. So again, using this latent variable model, the latent variables here are the user intent, whereas the observed variables are like behavior signals. For example, it could be the number of search queries on the platform, or a number of impressions, or a completion ratio, or things like that. You can define your own behavior signals based on your use case. And also, the contextual information could be very important, like in the example I just gave, like time of day or day of the week, and what device you are using, and the time since last visit. So basically, those variables together, they are observed. So we use them as observed variables to infer the user intent as latent variables. That's a very high-level summary of our approach. Excuse me. Sorry. I think the clicker doesn't really work. Oh. OK. Yeah, so the latent variable models are pretty well studied in literature, both in machine learning and in recommender system literature. But applications to a large-scale industrial recommender system is still pretty sparse. There are a few challenges, both from literature and from our own experience. And I listed a few here, and also how we mitigate those challenges. The first one is the training instability. So if you have worked with latent variable models, you might know that the training could be quite challenging, because most of the time there are different components of the model, and then it could cause training instability. So to tackle this problem, we introduced some specifically designed initialization scheme to make sure the training is stable at the beginning of the training stage. And also, we do some soft clipping to make sure it's also stable throughout the training. And also, another challenge is the interpretability. So because we are using this latent variable model, and then the thing we are inferring is something latent. So basically, there's no manually defined label to tell us what the latent variables are representing. So this is one challenge, not only for this approach, but in general for latent variable approach, is how to interpret the inferred latent variables. So here we propose to use a technique to look at the KL divergence. We'll talk more about that in a bit. And finally, many times the latent variable model approaches are quite complex. It will introduce more complexity to an industrial system. That's not a problem in a smaller scale experiment, but when you are working with a larger scale system, this introduced complexity can cause problem down the road. So that's why we have this design principle to make this user intent model or user intent module decoupled from the main recommender system, and then try to make it lightweight for easier maintenance. Okay, let's dive in a bit details into the connect. Okay, let's dive in the details to the technical design of the model. So we start with a probabilistic graphical model as our model assumption. So as I mentioned, we are trying to use this latent intent model to link the user intent as a latent variable with behavior signals as observed variables. So in particular, we are assuming that users' past behavior and the contextual information can affect users' current intent. And then users' current intent can be further manifested in users' future behavior. So this is essentially our modeling assumption, high-level modeling assumption in this approach. And then notice that for example, in your log data, you do have the observed past user behavior and future behavior. So those variables are essentially observed. That is denoted by the shaded nodes here, whereas the user intent is actually a latent variable. That's denoted by a transparent node here. So with this probabilistic modeling approach, the objective here we have is essentially trying to model the conditional distribution of the future user behavior conditioned on the past behavior. And then this distribution or this connection between past and future is mediated by the latent user intent. That's the high-level assumption of our probabilistic model. And then to perform training and inference, we are applying the variational autoencoder technique to train the model and then to perform inference. So for audience who are familiar with the variational autoencoder, the architecture we are using here is essentially the same as the conditional variational encoder. So recall that, let's go through the notations a little bit. So we use X to denote the past user behavior. So examples could be the number of searches or number of search queries or number of watches on the platform in the past 15 minutes. And then we use Y to denote future user behavior. That could be the same thing, number of clicks, number of searches in the next 15 minutes. And then we use Z to represent the latent variable. And then the model components, there are 3 model components, an encoder and decoder and a prior network. So the loss function has 2 components. The first one is the so-called reconstruction loss. So what it does is that given a pair of past behavior and future behavior, if you pass that through the encoder, that will give you a sampled user latent intent. And then if you pass that intent into the decoder, you will have a reconstructed future behavior. So if the model performs well enough, this reconstructed future behavior should be as close as possible to the true future behavior. So that's what we call the reconstruction loss. That's essentially the first term in the loss function here. So it's essentially saying that using an encoder-decoder technique or architecture, we can truthfully reconstruct users' future behavior. So that's one component of the loss function. Another component is the so-called regularization loss. So remember that we also have a prior network here. So the prior network is essentially given users' past behavior, what's our prior knowledge on users' intent. Whereas for the encoder, you can think of that as a posterior distribution. That is, after observing users' future behavior, what is your updated belief on users' intent? And then this regularization term is defined as the KL divergence between the posterior distribution and prior distribution. So it's essentially saying that we don't want the posterior distribution to be too far away from the prior distribution. And then the discrepancy here is defined by the KL divergence. So putting these 2 terms together, that's essentially the loss function for the conditional VAE or latent user intent module. So the loss function is also called elbow. that is the evidence lower bound, you can show that this evidence lower bound is actually a lower bound of the conditional log likelihood that we want to maximize. So essentially, we are maximizing the lower bound of the true conditional log likelihood. Yeah, so if you're familiar with the VAE literature, this is essentially the same as the conditional VAE model. Yeah, so as I mentioned, one design principle we have is trying to make this latent intent model as decoupled and as simple as possible so that it won't interfere with the main recommender system. So as I mentioned here, the use case we are applying this latent intent modeling technique is a sequential recommender system. So in this particular case, we are using an RNN to summarize users' interaction history on the platform. That will give us the final hidden state of this RNN is used as part of the user representation. And then together with other contextual information, we pass them through a feed-forward layer, which we call the post-fusion layers. And then that will give us the user representation. And then the way the latent intent model interacts with the sequential recommender system is that we only use the prior network to generate the inferred user intent, and then concatenate that intent with the existing RNN hidden state, and then pass that through the post-fusion layer to get the user representation. So essentially, we first, based on users' past behavior on the platform, we first infer users' current intent. And then that inferred intent is used as part of the user representation, which further affects the recommendation policy. Right? So essentially, we are conditioning the recommendation policy on the inferred user intent. So note that only the prior network is used here, because for the encoder and decoder, that would require the knowledge of future user behavior. But at request time or serving time, we don't really have that knowledge. What we have is only the past behavior. That's why we're only using the prior network here to interact with the main recommender system. So as I mentioned, one challenge with the latent intent model approach is the interpretability, right? So you can imagine that what we have is, given a past user behavior, what we have is just a vector to represent user's intent, right? It's really difficult to interpret this vector because we don't really have any labels to help us understand what the latent space is actually capturing. And one technique we borrowed from the existing literature is to essentially look at the KL divergence. So remember that the KL divergence is computed between the posterior distribution and the prior distribution. So in some sense, it measures the surprise of the surprise of the distribution, essentially. So when you observe the true observation, you have an updated knowledge of the user intent and how far away that updated knowledge is from your prior knowledge. And then if the KL divergence is large, it means that the surprise level is higher. So here we're trying to correlate this measure of surprise with a few variables, a few dimensions. For example, if a user consume a new item that the user has never consumed before, and then we compare that with the scenario where a user consumed an old item, that is an item that the user watched or listened before. So comparing the new item and old item, intuitively, if a user consumes something new, then the level of surprise should be higher, which is the case if you look at the first figure. We're comparing the y-axis is the KL divergence, and then the x-axis is the training steps through the training process. And then we have two curves. The yellow one represents the new item, and then the blue one represents an old item. So you can see that for the new one, the KL divergence is significantly higher than the old one. Similarly, instead of the item level, we can look at it from the topic level. Let's say if a user consumes an item from a new topic, the KL divergence is also higher than an old topic. And finally, we also look at search behavior. So those two curves represent whether a search behavior changed or unchanged. So a search behavior changed if before the request time and after the request time, the number of searches is different. So basically, if the user searched before the request time but didn't search after that, that's a behavior change, or vice versa. So we can see that when there is indeed a search behavior change, the KL divergence is higher than the unchanged case. So basically, this KL divergence analysis shows that the latent space actually can capture some important information about users' behavior. Sorry, next slide, please. Next slide, please. OK. And we also conducted live experiments to validate the effect of the proposed technique. So we conduct A/B experiments in a live system serving billions of users. And then, so in the production system, we use a very common two-stage approach. The first stage is the retrieval stage, and then second stage is the ranking stage. And then the model we described is actually part of the retrieval models. So essentially, we retrieve hundreds of candidates from the whole vocabulary, and then those candidates are then scored and ranked by a second ranking system before presenting the results to the user. And then for the A/B testing, we are looking at two metrics. The first one is essentially representing the user's overall enjoyment of the platform. And then the second one is the diversity of user-item interaction, because past analysis have shown that this diversity is a good proxy of longer-term user enjoyment. So that's why we're looking at this metric as well. And the control and the experiment model are essentially the same sequential recommender system with and without the latent intent module. And then we run this experiment for 3 weeks and then observe the effect. Next slide, please. OK. So here is the result of the A/B testing. So we're showing two metrics here. The first one is the overall enjoyment of users on the platform, and the second one is the diversity. So on the y-axis is the relative differences from the relative differences of the metric of the experimental model relative to the control model. And then on the x-axis is the date. And then we run the experiment for 3 weeks. So we can see clearly that the performance or the metrics are positive on both metrics. And then for the overall enjoyment, you can see there's an upward trend. So in recommender system, we call this learning effect. So basically, if you see a trend in the metric, it's indicating that the recommendation policy is actually affecting users' behavior. So that's a good thing we want to observe. Yeah, so overall, we can see that with this latent intent modeling approach, we can improve user satisfaction and overall enjoyment on the platform, both in the short term and in the long term, by the proxy metric. OK, yeah, so a quick summary. So we proposed this latent user intent model, which is a probabilistic modeling approach to capturing user intent as a latent variable. And then the latent user intent variable is further used to complement the existing sequential recommender system. And then the approach we are using here, the conditional variational autoencoder, is efficient and scalable. And we also validated the effectiveness of the proposed method on a large-scale industrial recommender system platform. And there are a few research directions. So as I mentioned, the interpretability of this approach is still a challenge, because still we want to better understand what the user actually wants from the platform. But with this latent variable approach, we only have a vector. It's difficult to interpret the inferred latent intent. So it would be great if we can use some other techniques, for example, the discrete latent space technique, to help us understand. So basically, if the latent space is discrete, your inferred latent user intent is no longer a vector, but it could be a bunch of tokens. So with these tokens, you can, for example, assign each token to a meaning or to a explainable user intent. That could help the interpretability of this model. And some techniques could be Gumbel softmax or VQ-VAE. Those can be applied here to get a discrete latent space. I think this is the last slide. Yeah, thank you everyone for your attention. And let me know if you have any questions, and take a look at the manuscript if you are interested. And yeah, looking forward to checking with you. Thank you.